Hello, welcome back. In this video, we'll discuss the multiferroics. The term multiferroic was introduced by Hans Schmidt in 1994. The multiferroics are those materials in which two or more ferroic orders such as ferroelectric and ferromagnetism they coexist. The examples for the ferroic orders are ferroelectric, ferromagnetic, etc. So in general, in any material, if two or more number of ferroic orders they coexist simultaneously, we call such material as a multiferroic material. In multiferroic, both orders may be in a single phase. So their technological importances are: they make it possible to control magnetic bit by electric bit, and secondly, the coupling of ferroelectric and ferromagnetic materials might give some novel properties which are not present in either state alone. And ferromagnetic materials might give some novel properties, and these properties they may not be available in the standalone materials. Meaning, if you have a multiferroic that can exhibit simultaneously ferroelectric and ferromagnetic properties, then such materials can give rise to some novel properties. These type of properties they make the multiferroics more energy efficient and useful in reducing the size of the storage devices significantly. We shall now see what is a ferroic. Materials which show long-range order with respect to at least one macroscopic property and develop a dipole with conjugate fields are known as ferroics. Materials that show long-range ordering with respect to at least one macroscopic properties and develop a dipole with conjugate field. A ferroic is a material that shows long-range order with respect to at least one macroscopic properties and develop a dipole with conjugate fields. There are four different types of ferroics. The first type is ferroelectric. The ferroelectric material which possesses a spontaneous polarization P that is stable and switched hysterically by an applied electric field E. A material which possesses a spontaneous electric polarization P that is stable and switched hysterically by an applied electric field E. Please recollect the BH curves are the hysteresis loops of the ferromagnetism. So the direction of the dipole moment or the polarization in the ferroelectric also can be changed using the principles of hysteresis. So we call such things as switched hysterically. A ferroelectric material which possesses a spontaneous electric polarization P that is stable and switched hysterically by an applied electric field E. The second one we discuss is the ferromagnetic. The ferromagnetic materials they possess a spontaneous magnetization M that is stable and switched hysterically by an applied magnetic field H. So ferromagnetic material possesses a spontaneous magnetization M that is switched hysterically by an applied magnetic field H. So the ferromagnetic materials they possess a spontaneous magnetization M that is switched hysterically by an applied magnetic field H. The third ferroic material is ferroelastic materials. The ferroelastic materials show spontaneous deformation that is stable and switched hysterically by an applied stress. Ferroelastics, they use the mechanical stress. Ferromagnetics, they use the magnetic field. They will have spontaneous magnetization. The ferroelectrics, they will have spontaneous electric polarization. The fourth one is, it is a state which is called as ferrotoroidic state. Ferrotoroidic state with a domain that could be hysterically switched space-time antisymmetric external field. The field we call as toroidal field. The field we call as toroidal field. As we have seen before, a multiferroic material is one in which two or more than two ferroic orderings they coexist. Multiferroics classified into two types, type 1 and type 2 multiferroics. We'll discuss first the type 1. If the magnetic and ferroelectric ordering in the material occurs independently, that means the source of ferroelectric ordering and magnetic ordering are different, then they are denoted by type 1 multiferroics. So if the magnetic and ferroelectric ordering in the material occurs independently, then we call such multiferroics as type 1 multiferroics. And in type 1 multiferroics, the coupling between the magnetism and ferroelectricity is usually weak. In type 1 multiferroics, the coupling between magnetism and ferroelectricity is weak. Now we shall look at the type 2 multiferroics. If the ferroelectricity and magnetic transition emerges jointly, then we call such multiferroics as type 2 multiferroics. Magnetic transition emerges jointly, then we call the multiferroics as type 2. In case of the type 2 multiferroics, the coupling between the magnetism and ferroelectricity is larger than type 1. The coupling between magnetism and ferroelectricity in type 2 multiferroics is larger than the type 1 multiferroics. In this video, we have said that the term multiferroics was introduced by Hans Schmid in 1994. We have said further that multiferroics are those materials in which two or more ferroic orders coexist. We have seen the examples for the ferroic orders. They are ferroelectricity, ferromagnetism, etc. There are certain technological importances with the multiferroics. They make it possible to control magnetic bit by electric bit. Secondly, the coupling of ferroelectric and ferromagnetic materials might give rise to some novel properties. We have seen what is a ferroic. We have said that material that show long range order with respect to at least one macroscopic properties and develop a dipole with conjugate fields are known as ferroics. There are four types of ferroics. We have seen the ferroelectric, ferromagnetic, ferroelastic, ferrotoroidic state of ferroics. Type 1 and type 2 multiferroics we have seen. If the magnetic and electric ordering in the material occurs independently, then we call such multiferroics as type 1. In type 1 multiferroics, the coupling between the magnetism and electricity is weak. If the ferroelectricity and magnetic transition emerges jointly, then we call the multiferroics as type 2 multiferroics. In type 2 multiferroics, the coupling between magnetism and ferroelectricity is larger than the type 1 multiferroics. Thank you.